All right, hello everyone. November the 10th. All right, we have an easy problem again. So let's finish this and we're gonna try this one. Okay, remove duplicates from sorted array. Given an integer array sorted in non-decreasing order, so it's increasing and in the same. Remove the duplicates in place such that each unique element appears only once. The relative order of the elements should be kept the same. Since it is impossible to change the length of the array in some language, you must instead have the result be placed in the first part of the array. Well, formally, if there are k elements after removing the duplicates, then the first k elements of num should hold the final results. It does not matter what you leave behind. First k elements. Return k after placing the final result on the first k. So when return k. Wait, hold on. What the hell is k? Removing. Okay, I see. Do not allocate new space. Modify in place. Okay, 1, 2. Yeah. Okay. All right. So we do it in place. So what do we do? Let's find a new one, move here, and then keep going. If it's the same as this, we keep going. When it's not the same, then we do here, move forward. No, don't move forward, stay at the same position. And so we find the same, just keep moving. Once it's not same, move forward, put it here, and then move forward. So it's like, what is this type of technique? We call it two pointers. This is a two-pointer problem. Okay. We have I, J, 0 and 1. Actually, I think it should be the same. If they're the same, then we'll move forward. No, don't move forward. If they're the same, then J move forward. If they're the same, J move forward. Yeah. So while J is smaller than nums, if nums J is equal to nums I, then J plus equal 1. Else, if they're not the same, I plus equal 1, nums I equals nums J. And then J plus equal 1. So in that case, we will do something like that. And then we'll return I. All right. Let's see. That is not correct. Okay. I'm missing the last one. J plus equal 1. If they are the same, J plus equal 1. Right? And then if they're not the same, I plus equal 1. And, so I think it's I plus 1. Let me see. Yeah, because what I'm pointing at is the previous one, right? So if I do this, It'll point to the last one, but I want a total number. So yeah, I think this should be right. Okay. 2 pointers. Wait, hold on. When did I do it the first time? Oh, first time, 2018. 2018. Oh, that was C++. Ha. That was C++. Yeah. Can I still code in C++? Well, give me a few weeks. I think I'll be able to. 2 pointers. Okay, so that's that. Let's see this one. You're given a zero-indexed integer array. The number of ways to partition the nums is the number of pivot indices that satisfy both conditions. Pivot has to be inside, but not the first one, but it can be the last one. Nums 0 blah 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 plus all the pivot equals pivot to the end. So okay, you're also given an integer k. You can choose to change the value of one element to k, or to leave the array unchanged. Return the maximum possible number of ways to partition nums to satisfy both conditions after changing at most one element. So pivot to the end and before. So the before has to equal to the end. And we want to know the maximum possible number of ways to partition nums to satisfy both conditions. So how many different ways if I partition it after I change at most one element, and after I change it, how many ways? Like in this one, initially I can only partition on this one and this one. If I partition on this, it's 2 and 1. If I partition on this, it's 1 and 2. So both are not right. And if we change this to 3, then we can partition here, so we have 2 and 2. Okay, how about this one? If I don't use it, I can partition in here and partition in here. Gotcha. Okay, this is a good test case. I'm not even going to see it. But there are 4 ways to partition it. Okay, so what we want is the maximum number, dp, yeah. So it's a dp problem. We just need to find the conditions that can lead us to the correct answer. So we have an array, right? And we want to know the partition, which means what we can build is we might need bit for this, easy access. So like we can change one and then query to be very fast. So yeah, bit is the way. However, do you still remember how to do bit? That is a good question. Yes, maybe. Maybe I do, maybe I don't. But bit is kind of the idea. And then what? We try every single one? Yo, man. No, because you can change 10 to the 5th, okay? 10 to the 5th. You can change, I change the first one. And we are asking how many ways we can do it. I mean, we can change the first one, we just update that. And then we start from here, we try to see this, like this compared to this compared to this, and then we try to see if any of them is equal, and then I change the next one. Now, but we do see, right? We do see a lot of duplicated computations, because if you change, let's say you change the first one, right? And then you change the second one, then almost all of them are the same, right? The partitions are the same. So what I would say is that we can have the partitions. We can have a left and a right. Okay? Let's say we have a left and right. The left half, we can start with 1, and then 2, and then 3, all the way to 1 minus 1, right? And the right will have minus 1, n minus 1, and n minus 2, we have 1, right? We have this is the initial one, and we can get this initial one easily, right? We can get this one easily. Okay, so the position of partition, now we can just do it at that. The position of partition, the exact position of partition. So with that in mind, what we can do is we can find how many are equal at this moment. So that will be like 0 change. And then we need to implement change at each position. And if we implement change at this position, let's say if I implement a change somewhere, right? If I implement change here, then all the partitions before it, all the partition to the left will be impacted on the right side. All the partition on the right will be impacted on the left side. So what we can do is to find the delta, right? So when we can find the delta is the original, the left minus right. What is the delta? Okay, so if we say we have a left minus right for at each partition position, right? If we have at each partition position starting from 1 all the way to n, so we have 1, 2, to n. So we have a d1, d2 all the way to dn, right? This is again something we calculated from the previous. And once we have that, now we have the new thing come in. I say I want to change at position 1, right? Then what happens? Then we can calculate the delta. The delta is just minus the original and a plus the current. So we have the delta, the d, okay? And for changing this, everything to the left is going to be, wait, hold on, let's do this one more time. So we changed it here, right? So it's everything to the right, So the partition is from 1, right? So 1 towards that value, okay? The partition from 1 towards that value. So the partition, let's say we change an I, right? We change an I, which will cause a delta of D. And from 1 all the way to I, what happens is the left stayed unchanged, but the right need to plus this delta, right? The right need to plus this delta. So now what we need to do is to find from 1 to I how many of the original deltas, which is left minus right, right? So say left minus right equals d1, and I want this to become 0. So it has to be, so the current delta needs to be, so hold on. So now we have left minus right equals d1, And now right becomes right plus d. So it becomes left minus right minus d, right? We want this to be 0, which means we want d1 minus d to be 0. So we want d to be d1. So we want to find among from 1 to n, how many of them are d, are the current d, right? And then if we make the count, and then once we pass it from partitioning from here all the way to I, right? All the way to I is affected on the right side, but passing I, so we say from I plus 1, right? Partition from I plus 1, if it's the I plus 1 position, like the partition is that if it starts at I plus 1 position, and all the way to n minus 1, right? All the way to n minus 1. Then the right stayed unchanged. And it's the left has to plus this d. So now the formula becomes left plus d minus right. We want this to become 0. And again, left minus right is equal to d prime, the original one. So it's d prime plus d equals 0. So we need to find minus d. And the original one is find d. All right? So now we need to know among all the difference, among all the deltas from what? From 1 to I plus 1, from 1 to I, right? I is passing I plus 1. From 1 to, yeah, for each position, right? From 1 to this position, right? This is I position. From this to this, we need to find the number of D's. And then from I plus 1 to the end, we need to find, wait, hold on, let me do this one more time. So we are at this position, right? And we say, if we do all the partitions here, yeah, so from that position, I plus 1 towards the end, from I plus 1 towards the end, we want to find among them the number of minus D's. And then we can add them together. So now the question is, how many are there? Right? That's what we want to know. How many are there? So if we can line them up with d1, d2, to di, right? And the di plus 1 to dn, to dn. It's actually not dn, it's dn minus 1. Because the last partition is at n minus 1. Right? So we want to find among these how many are d, and among the remains how many are minus d. So how do we solve this? Well, I don't see us do a counter every single time, which will be easy, but a counter will turn this into, hold a second. We want to know the count. But if we do a counter, it will consider the whole thing. But would it? If we go one by one, we can have two counters. One for the first half and the other one for the second half. And then as we go through the first half, we just keep adding, right? And then on the second half, we just keep removing. I'm telling you, man, this seems to be very likely. I think we might have a solution for this. (2025). Damn, 2025 is almost there. Well, we still have to go through 2023 and 2024. So we're still in 2022, but 2022 is coming to an end. Yeah. We need counter. Okay. So what do we do here? So we have all of these. So the first thing we need to do, Right? The first thing we need to do, we need to find the differences. Okay, so the diffs, right? The diffs is going to be a this, okay? And then what we need to know is the sum of everything, okay? We can say SL and SR, right? SR equals to, and then the first one we call it 0, right? But we don't use it. So SL is nums 0, SR is sum nums 1 to the end. Then we say for I in range from 1 to len nums, let's put len nums into an n. Okay, so 1 to n, we say diffs dot append SL, well, we do SL minus SR, okay? And after that, we say SL plus equal to nums I, and SR minus equal to nums I, right? So because we are moving forward every time, because that's the, initially SL and SR is the first partition, right? We put it in, and then we move here with the minus here, and the second one, all the way to the last one, when I is n plus 1. So when I is n plus 1, so the previous step will be this one plus this, right? This one minus this. So SR should be the last one, SL is this one. And then we put in the last one, right? And SL, and then SR should be 0 actually at the end. So we come out. So this is our diffs, right? The original diffs. Now what we need to do is to run the same thing again, but we have counter left and a counter right. So the counter left and a counter right is going to be it's going to be a counter, right, of diffs 0. That's the no. Don't do this. Do math.inf, so we're not hitting anything. So we can say this to 1. Well, actually, no. 0, 1. It actually have to do 2. But honestly, it doesn't really matter, you know. It doesn't really matter. Yeah, it doesn't really matter. We can now we just leave this one here. Now this we're gonna do with 1, because I already put in there, right? There's a counter on the left, and we have a counter on the right, which is diffs 2 to the end, right? So we have 1, now we have 2 to the end. So that's our starting position. And now we can say for I, right? We say for I in range from 1 to n, and each time that's the position we're going to make change, right? We're going to make change. Then we say the delta is equal to, we're going to minus nums I, but to plus k minus nums I, right? Plus k minus nums I, this is the delta. Then what we need to find is on the left, on the right, how many, right? Then we can say, what we can say is res is the original value, is this 0 plus right 0 without changing anything, right? Now what we're gonna say is res shall equal to maximum res, because we're looking for the maximum value, right? Maximum value of CL. So on the left we need to find D. On the right we need to find minus D. That's what we have concluded, right? What we have concluded. And then once we're done here, we say CL something, right, plus equal 1, and then that something is going to be what is that something's going to be? Because we start at 1, okay? We start at the first partition, which means we start at this, right? if you think about it, the diffs, right? With diff, we have at this partition, we have a diff, right? We have a diff. So this diff and this diff and this diff, right? So we now have, we are at the first one. And then, you know what? I don't think we should start at 1 because we're already done here. So we actually should start at 2. But we are computing on this thing. We're computing on this thing. We're making changes. And this is actually correct, right? But then what? To move to the next level, to 2, which means we shall include this and then I plus 1, right? We shall include this. So now is I1, we do this. And then now is 2. So when 2 comes in, we shall include everything, right? We shall include the 2, which I think we shall do it slightly differently. I think this is what we need, right? So when a 1 comes, we say CL diff I plus equal 1, right? Because I will move this here, and then CR diffs I will be minus equal 1. Then we do this, right? Then we do this. Because the first one is on index 1, right? On index 1, we want to find all the difference. When we split on index 1, and we split on index 1, and we have the diff when we split on index 1 at diffs 1, right? So we need to add that diff to the left side, which is not changed, right? Yeah, the left side is not changed. No, the right side is not changed. If we have changed this thing, right? If we change this, I had it right earlier. If I change this value, then all the diffs from before, this to the end, this to the end, this to the end, they don't change. That's the left side. If the partition is on the left side, right? If the partition is on the left side, then we don't change, right? And then what we're saying is if we do on this point, right, we make changes for this, and then we have the counter of all the partitions on the left, right? All the partitions, like everything on the left, and then they do not change. And all the partitions from this to the right, they all have to change. So we will say for all the partitions on the left, yeah, we make changes to this value, right? So we use this value as the splitting point, the partitioning position. So if the partitioning happens here, then the difference, then the difference is going to be this, yes. And the partition is on the right, which is after this, because we including the partition here, right? And the partition after is I plus 1. If the partition happens here, then it's slightly different. So now we calculate this and then we move forward. So I think this is correct. So we add the difference of the partition at this specific value, right? And that's considered on the left side, right? Which requires to be a D. So at the end, we're gonna return res. Let's just check. This is a lot of logical things to go through. I don't know, but I have confidence that even though this is not correct, I'm very close to the truth. It just fit all the bills, you know, the requirement of how it should be. It just fit all the requirements. Ways to partition. Okay, it's not right, but I still hold true to my belief that we are close. See, that is correct, right? So now what we need to do is, I want to print our diffs, just kind of see. So diff is, if I here, the diff is 1. If it's here, the diff is -1. That is also correct, okay? So just write it out. So we have our diff, okay? This is our diff. We have this position is 1, this position is -1. And what we're saying is, if we change the value here, and then change value is 1, right? Then we say, it's gonna be -1 and plus 3. Right, this is gonna be +2. And then in the first position, we want to find a +2 on the left. Right, on the left we have 1, on the right we have a -1. Right? That doesn't work. We actually see, let's print CL, CR, and D. CL, CR, and D. How is D faux? Oh, the position. Damn. I think it should be I -1 here. Because I'm splitting on diffs, right? So the 1, the value that I actually change, hold a second, the value that I actually change, the value that I change, it shouldn't be a 4. No, there will be a 4. Should be a -2 and a +3, right? This is the partition, okay? This is the partition. So if I change, hold on, let me think about one more time. If I change on this value, okay? If I change on this value, then the partition here, right? And the partition here, the front all doesn't matter. It's on the right side. Like all the changes on the right side. So if I partition here. So if that's the case, but and hold on. What if I change the first value? If I change the first value, because the partition can only start from here, right? If I change this value, it's the same as I change this value, right? No. If I change this value, that's a special case. Because that only changed the front. Yeah, because I partition here, I change the front. It doesn't change the end. Just like if I partition here, no, if I change here, then all the partitions will have, right, it's only like these don't change. So I have the difference. Oh wait, hold on. I can do this. I have the change of I have change of this minus this, right? And then this minus this, this minus this, this minus this, right? I have all of these values. And then I'm saying if I change the first one, right? if I change the first one, then everything to the left, but there's nothing to the left. There's only things to the right. Okay, there's only things to the right. There's nothing to the left, which means it's gonna be a left plus d minus right situation, right? Left plus d minus y situation. So that's when I equals to 0, it's gonna be this. But when I equal to 1, which I change this value, then we have a chance of a left, right? Then we have a left, and then we have a right, and the right is everybody. And if I change this value, right? If I change this value, then the partition from this, because partition from this, partition from 1, 2, 3, all of them, right? They are changed, but the left isn't changed. It's the left minus right minus d. So we need to find the difference, the left and right difference, to be equal to d, right? Starting from this to the end. On the left side, no. The left side, which is partitioned on this side. Hold on, I got this. So we have a partition in this position. Not a partition, we have a change of value in this position, right? I have a change of value in this position. If I change a value in this position, I say the partition from here, like if I do partition here, right, the left doesn't change and the right change. Partition here, left doesn't change, right change. Partition here, left doesn't change, right change. All the way to partition at this specific position is left change, but right does not change. Right? The left change, the right does not change. And we go on. So what I think, we should start from here, right? And then d is equal to this. And CL is nothing because we don't have any left. We do once we change this value on the left. There's nothing on the left. Everything changes is on the right. No. Everything changes on the left and nothing changes on the right. Right? So we say on the right is diffs from 1 to the end. So none of them change. Right? None of these change. But the diff on the left, there's no diff on the left. Right? There's no diff on the left. So we'll do this. And once we're done, then I is 0. Right? Once we're done, then we'll change this value, right? When we change this value, then we change this value, the first one, we change that value, then the diff at this, these are all the left change, now the left change, this is the left change, this is also the left change, but this is the right change, right? And this, so we're going to put a diff on the left hand side, right? Which the left hand side is the left change. No, the left hand side is the left does not change, the right change, right? The left does not change, but the right does change. And if we go here, it's different, right? So we're going to say like this. We put the difference in it. We put the difference in it. So next time when we do the change, we change this, right? We change at this position. Then on the left side, which is left doesn't change but right change, now how many differences do we have? So if in this case, then we pass. Then we pass all of them. Nope, didn't pass all of them. We passed 2, we fail 1. Okay. Okay, that's unexpected. Okay, the diffs. So this is the first, right? It's this and this. So we have minus 37. Oh, CR. No. But that was wrong. It's supposed to be CR. No, the first two still pass. Answer is 2. I see 20. It's probably one of the positions. Which position it is? On the cusp. We have a 2. Change the second one. I don't see any benefit, which means our ways might not be right. Shoot. if we change minus 25 to minus 33, that is taking away minus 8, right? It's minus 8. So which one is it? Which one is it? So when I is equal to 2, right? When I is equal to 0, 1, 2 is equal to 2, that should just, when I is equal to 2, yeah, that's the current situation. On the left, we have this and this. Hold on, let me see. Right, so I say, if I partition in here, you know what? Stupid. What's that? Accumulate. Okay. That is a very interesting result. S left minus S right. Minus 46, that's correct. So the left minus right. Lord, it is 90. Okay, so if I change this one from minus 25, I mean everything will change, right? Because this changing the minus is just minus 25 plus minus 33, so that's minus 8. So everybody will minus 8. So this way all the way adding to this will be minus 8. This will be minus 8, which, hold on. Can do this, yeah. So it's 134. I saw the 52s. I think that is the key. Yeah, because if one of them works, maybe they all works. Okay, so what I'm changing is 0, 1, 2. So this is 2 is here, right? This one's what's affected when the partition is at 2, right? This is a 1. This is a 2. 2. Oh, I think I saw the problem. This is still 1 to the end because I handled 0 already. I handled 0 already. So we have to go from 1. Then we have an issue here. Wait, no. No, this is the first partition, right? This is the first partition. And what we can do is, let's do this as 0. This is sum everything. And I put this one here. Okay. There we go. There we go. We have some issues over that thing. There we go. There we go. Yeah, I told you. I told you. So it's exactly the same method if you think about it. All right, so want to run some random values. Get a kick out of it. Yeah, my answer is why not? Let's do 100. Minus 100 to 100. Actually, minus 22. That's okay. 2 to 100. See. Confidence. Boost. Come on. Come on. No. No. I have a confidence boost. But it's wrong. That's unfair. That's not fair. Okay. We're gonna reduce this. Just trying to see if there's anything we can get out of this. How do I can't. This is ridiculous. Nope. How do I copy and paste directly from here? Nah, that's not the way to go. Okay. I can't even move the things around, so it's quite stupid. But it's fine. I can do this. Right, I just want a lot of test cases to help me identify if there is anything worth trying. If none of these give me any result. Oh, good. Got 2. But Lord, where are they? Where are they? You know what? That was a stupid way to do it. We're gonna go binary search. Okay, binary search. Perfect. Look at that. Using binary search to find the solution. Nope. Then Control Z. And we'll remove the top half. Yeah, definitely it's there. But maybe we have small enough number we can figure out where the arrow is. Oh, the last, not the last 2, but the third. Not this one. This one's good. These 2. Mamma mia. Let's do this. Okay. Yeah, this is a stupid way. Don't do it. Don't do it. Okay, so this one is wrong. This one is wrong. Of course, we also have the official solution is also wrong. Output 0, 3, expect a 1 and 2. 1 and 2. Okay. This is supposed to be 33. I got 34. There we go. Okay, let's see. Result 0, but supposed to be 1. Okay, okie dokie. So what we want to do is to find out where, right? Where exactly are we talking about? So first of all, I want to find a diff to see if it makes sense, right? So we're gonna print diffs, right? And then I'm gonna say L equals list accumulate. All right, we need to make sure that everything is fine. And then for I in range 1 to n, print L I minus 1. Well, actually, let me just go do this. I want to print this minus L minus 1 minus Li. Wait, what? Are we supposed to have one more? This minus Li is this. That's the first partition, right? And then we have the last partition is on the last one, which is I is here. So this minus this minus this. So that's true. But in reality, my diff is one more. Huh. That is strange. Oh yeah, it has to be minus 1. But anyway, these two are match. Okay. Now we're gonna take a look at this thing. And what I'm just saying is, but I can take the last one. The diffs. Shouldn't this be the whole thing, huh? Right? And then for I in range, so I change the first value, okay? Change the first value, but it doesn't matter. If I change the first value, say our D is always going to be 0, it's on the remainder, right? If I change this, we'll find that. And then I'll change this value, right? The diffs, I will put the diffs on 0. Now I see why. Need to put. There we go. That's right. That is right. What? What? Oh man. How? Dude, man, how did that happen? Oh, because that's I. And diff I. It should be fine. Oh, we're doing diff 0. Nope. That's not right. So we handle the first change, right? Then after we do that, we're gonna move on, right? This and then that. I'm gonna move on to this change. And when we move on to this change, wait, this is fine because k is minus, that's the num, right? And then diffs1. Diffs1 is our first diff, right? Diffs1 is our first diff. So okay, diffs1 is our first diff. We do diffs1, and then on the right side we remove diffs1. Then for the first diff, right? And the left side we have if I change this value, right? Then the diff when we partition here, when we partition here, right? This also left doesn't change. We partition here. Because it's I minus 1. I think it's just one of the i's. Yeah, pivot minus 1. So I partition here. This includes, and then this doesn't include, right? So we have all the values. If I partition at 1, we have this and this the difference, right? And if I change this value, then on the left side, it shall be the diff, the original diff. Is it? Is it? Is it? Yes, it is, because the change happens on the right side. It's not happening on the left side, right? So the first one, change happens here. So the diffs of these two, including here, right? So which means if I make changes here, the I can do 1 to the end. You're saying if we take this into a 3, and we can partition here, that's 1. Yeah, we have 1. This last situation doesn't exist. Makes sense now. Let's try it again. Nice. Nice. All the difficult cases passed. I think I can write. Yeah, this is a good question. It's not difficult, but it's quite complex for me. Now the idea is that once we change a position, right? So change a position. Once we change a position at j, at j, for all the partitions in 1 towards, actually I have to do I, for all position from 1 towards I, the left half, the sum, right? The prefix sum, the sum of the left half stay the same, whereas the sum of the right half changed by a delta equals k minus nums I. Similarly, for all the partitions in I, not partition, for all the pivots at, right? All the pivots, I plus 1 towards n minus 1. The left half changes by delta, whereas the right half stay the same. If we pre-compute, right, all the differences at each pivot position, right, and make that into a diffs, d1, d2, dn minus 1, right? Then after a change, if we want the partitions caveats at 1 to I to form a good partition, we must have left minus right plus d, right plus delta equals 0, which have delta equals left minus right. In other words, the number of good partitions is the count, right, of inside is the count of d1, d2, right, d I to di that are equal to delta. Similarly, if we want the caveats at I plus 1 to n minus 1 to form a good partition, we must have left plus delta minus right equals 0, which is left minus right equals minus delta. In other words, the number of good partitions is the count of di plus 1 to dn minus 1. Yeah, to d that are equal to minus delta. So yeah, this is the base of our thing. Now this is based on this, we use a left sum and a right sum to compute. We progressively build a left sum and right sum to compute the diffs array, and then use a left counter, and then progressively build a left counter and a right counter to compute the number of matches to delta and minus delta at each position, at each when number is changed at each position I. Now the difficulty is in the implementation. Especially with the indices. Yeah, this is to prevent error in the second half. And the counter arithmetic. Okay. Last check. Good. Submit. There we go. Good. Good. ON and this. All right. That will be it. I'll see you guys tomorrow. Adios.